Okay, so today we're going to be furthering our understanding of Gibbs free energy. We're going to be looking at how temperature affects the value of delta G and calculating the temperature at which a reaction becomes feasible. So the first thing that we're going to do is to work out how we can use this equation to calculate the temperature at which a reaction just becomes feasible. Now, for a reaction to be just feasible, delta G is going to have to be equal to 0. So we can write this equation as 0 equals delta H minus T delta S. Now, we want to calculate the temperature at which it becomes feasible. So we want to make temperature the subject of that equation. So I'm going to rearrange this equation first of all by taking minus T delta S over the other side, which becomes plus T delta S equals delta H, and then rearranging the equation so that temperature is the subject, and we have T equals delta H divided by delta S. So you can remember this derivation, or if you want, you can just remember this as a second equation that you need to know, and this is the temperature at which the reaction becomes feasible. So where delta G is equal to 0. So remember that temperature is the temperature at which a reaction could occur, the minimum temperature or the maximum temperature at which a reaction could occur. There are other factors to consider though. So simply because a reaction is feasible doesn't necessarily mean it will occur, because the activation energy might be a barrier to that happening. So let's have a look at doing this in practice. So I've got an example question here for us to have a look at. We'll just talk through some key points. It also allows us to revise some things that we've looked at. So here's our reaction. It's an equilibrium for the reaction of methane with water to produce carbon dioxide and 3 moles of hydrogen. The first thing we've got to do is calculate the enthalpy change for this reaction. So it's a good opportunity for us to revise some things. So if we want to calculate the enthalpy change for that reaction, it's going to be the sum of the enthalpy change of formation of the products minus the sum of the enthalpy change of formation of the reactants. So here are our products, here are our reactants. So we're using enthalpy change of formation data, so one of these values is 0, and that's obviously because by definition you can't form an element in its standard state from itself, or the enthalpy change would be equal to 0. So in fact we can ignore this, and the enthalpy change of reaction is equal to the enthalpy change of formation of the product, which in this case is just 1 mole of carbon monoxide, minus the enthalpy change of formation of methane and the enthalpy change of formation of water, which gives us 206 kilojoules per mole. Remember, the units are going to be important later because we might need to do some conversions. So the second part of our question is asking us to calculate the minimum temperature in degrees Celsius needed for this reaction to become feasible. And there's a last little bit to our question, which asks us to give the answer to an appropriate number of significant figures, which we'll deal with in a minute. So we've already derived that equation for ourselves as T equals delta H divided by delta S. We know delta H, we've just calculated it. We haven't yet got delta S, so we're going to need to do that part. So delta S is equal to the sum of the enthalpy change, the sum of the entropies of the product minus the sum of the entropy of the reactants. So using the data in the table, that's going to be, sorry, I can't quite get all of that on here. I'll just talk through it and then actually put the values down. So the entropy of the product is 1 CO and 3 times 313. Sometimes it's worth actually putting that in there to help you, minus the entropy of methane and the entropy of water. So let's actually put those together. So that's 3 times 131 plus 198. So those are the products. And we're taking away from that the entropies of the reactants, which is those. And that gives us an entropy change of 216 joules per Kelvin per mole. So this is in joules. Enthalpy change is in kilojoules. So we're going to need to convert one of them. And the one that we're going to convert is this one. So our final answer is 0.216 kilojoules per Kelvin per mole. And that's the answer that I'm going to need. Remember, I did that divided by dividing this by 1000 to give it to us in kilojoules per mole. So it's always worth us just thinking as well, that's a positive entropy change. Let's have a double check if that's what we'd expect. Having looked back at the equation, we've got 2 gaseous molecules going to 1, 2, 3, 4 gaseous molecules. So we're going from 2 species, all gases, to 4 species. So we're expecting this to be more disordered. Is that borne out in our value? Yes, it is, because we've got a positive entropy change here. So let's do the last part of our calculation. So T equals delta H divided by delta S. So T is going to be equal to delta H, which we calculated earlier, which is 206 kilojoules per mole, divided by 0.216 kilojoules per Kelvin per mole. And that gives us an answer of 954 kelvins. So it's actually 953.7 kelvins, but we've rounded it up to 3 significant figures. We'll talk about why that is in a moment. The important thing to us to recognize is this is in Kelvin. So notice I've left the units in here. Entropy is in kilojoules per Kelvin per mole, which means that this temperature change is in kelvins. We're going to need to convert that into degrees Celsius because that's what the question has asked us to do. So we're going to subtract 273 from that, which then gives us a final answer of 681 degrees Celsius. So that's how we do one of these calculations. The last thing we need to have a look at is the temperature dependence of our reactions. It might be at this point that you want to pause and maybe look at the rest of the video separate to this. Right, so there are 4 types of chemical reactions, and they're going to affect the feasibility of our reactions, so feasibility at different temperatures. A reaction can be exothermic, in which case it will have a negative delta H, or it can be endothermic, in which case it will have a positive delta H. For each of these reactions, there is also a reaction that increases entropy plus delta S, or decreases entropy minus delta S. So our 4 types of reactions: exothermic with an increase in entropy, exothermic with a decrease in entropy, endothermic with an increase in entropy, endothermic with a decrease in entropy. Let's have a look at what happens to each equation. Delta G equals minus delta H minus T plus delta S. Okay, so this is a negative value because it's an exothermic reaction, and I put this in here. Put the positive delta S in there, which means that the reaction is effectively minus delta H minus T delta S. It doesn't matter what value of temperature we have, delta G is always less than 0. So this type of reaction is always feasible at whatever temperature. Let's have a look at this one. Delta G equals minus delta H minus T minus delta S. So I've put minus delta S in there because this reaction is a decrease in entropy, which means if I substitute out the minuses, minus T minus delta S means plus T delta S. So as the value of T increases, the value of delta G is also going to increase. So delta G will increases as temperature increases. Remember that as delta G increases, the reaction is going to become less likely, and we'll get to a point where delta G becomes greater than 0, and therefore we can say that the reaction is less feasible as temperature increases. Let's have a look at this one. Delta G equals plus delta H. So this time we've got an endothermic reaction, so it's plus delta H minus T plus delta S. Let's substitute the values out. Plus delta H minus T delta S. So delta G decreases as temperature increases. So the reason is, as this value goes up, we're subtracting a increasingly larger value from delta H, which will be a constant, and delta S, which will be a constant, and therefore the reaction is more feasible, or more likely to be feasible, as the temperature increases. We'll get to a point where the value is positive and then it slips below 0, and therefore it's more likely to become feasible. Our final example, delta G equals plus delta H minus T minus delta S. We've got a positive delta H, we've got a negative delta S. So delta G equals plus delta H plus T delta S. These two minuses give us plus T delta S. Delta G is always greater than 0. Doesn't matter what value of temperature we have, delta G is always greater than 0. This reaction is never feasible. So if we look at our two extremes, an exothermic reaction with an increase in entropy is feasible at any temperature. An endothermic reaction with a decrease in entropy is never feasible. And then we've got our two intermediate reactions here, and their feasibility changes depending on temperature. Thank you very much.